Hi, everybody. Apparently this is third take, but I'm going to be doing this relatively testing kind of thing where I'm going to talk about the problem of tiling squares with polyominoes. Specifically, I'm thinking about small polyominoes, polyominoes which are small enough that are interesting to consider, and I'm considering like for a specific polyomino, which squares can you tile? Um, so that's the problem that I'm going to try to consider here, right? So, for instance, I mean, there are some results that that are pretty famous, even though they're not technically squares. So here I have an 8x8 grid, right? And then I can take away these two corners, and it's relatively famous that if you take polyominoes, specifically dominoes, like these ones, then you cannot tile the entire board with these dominoes. You can try, but you find that after you tile the majority of them, there isn't enough space. So specifically, if you tile them, you'll get one here, 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 and then down. And then you'll find that here you have a missing space over here, and whatever you do over here doesn't matter, and you're not going to be able to cover it in this pattern. And there is a proof for why you can't cover it. And specifically, it has to do with coloring. And it's if you color every even one in a specific color. So let's say if I color these black, then I can do this kind of checkerboard pattern in which each domino, I'm not going to do it for the right half, but in which each domino covers one white and one black square. And the entire board here has 32 black squares and 30 white squares. And therefore, since each domino covers one black square and one white square, we're going to take 31 dominoes to cover 62 squares. But that will cover 31 black squares and 31 white squares instead of the 32 black squares and 30 white squares. So that is the rationale. Okay. Now, I want to talk about specifically, we're going to limit our scope to squares because once you get to bigger polyominoes, then it's harder to analyze. It's harder to analyze non-square shapes, right? Especially weird shapes. And I did consider doing this for rectangles, but it didn't quite work. So we're going to be doing squares. So, continuing back, we're going to start from the simplest polyomino, arguably the monomino. Anyone has a guess for what squares a monomino can tile? I guess
Any?
it's not that hard.
When you say squares, are we only considering like n by n squares? Is that the question here?
Yeah, n by n squares.
Okay.
Yep.
Yeah, then all of
By
them,
n
I
squares
guess.
for positive integer.
Cool.
Lattice confined monotile. I'm not sure how that would work. But okay, I'm reading from the chat. Natalia is saying, what about tiling squares with basically tiling really big tiles and trying to encode. I'm assuming trying to encode some satisfactory problem inside there. I think that's interesting, but I don't really see how it can be done. But yes, one by one squares, right? And one by one squares can tile all squares. One by one polyominoes can tile all squares. Easy, yay. Now let's consider dominoes. And because it's squares, the result is kind of still very easy. Any guesses? I guess.
Only even n.
Yep, only even n. And right. So I'm gonna outline the proof. The similar proof is probably gonna come up like if you want to do it rigorously, it's obviously gonna come up like a bazillion times, and by a bazillion, I'm thinking like 10 throughout this talk. But basically, if n is odd, then you get an odd total number of squares. That's obviously not tileable with an even number, with an integer number of dominoes, because you're going to be tiling an even number of squares. And so it has to be an even by even. And for an even by even, you just make a construction, and the construction is trivial because you can just tile it in 2 by 2. I can call it monomers, but that's like a biology term. I'll call these units, right? I can tile these with these 2 by 2 units, and that will allow me to tile any 2 by 2 square. Yep. Next up, 1 by 3. Right. For 1 by 3, I guess I'll 3n by 3n, as in the chat. Again, the proof is easy. If it's not 3, that's obviously not possible. Otherwise, we built this structure. The more interesting tromino is, well, the other tromino, and that's going to be, if this decides to work, the L tromino, right? And I was gonna attempt to draw this here, but it looks like this. Any guesses for what the L tromino can tile? And this is, I think, significantly harder.
Yeah, I'll need a minute to think about that.
This is what this entire talk is probably going to be. I have no idea why this is just not choosing appropriate. Can try 6n by 6n. The construction is obvious, and because Excalibur isn't allowing me to create a new shape, I'll have to do with this. You can have one here, and then this is a 2 by 3 unit. So if you repeat this 2 by 3 unit 6 times, then you get a 6 by 6 unit, like this. And so it can tile a 6 by 6, which means it can tile a 6n by 6n. Yeah, disregard. Yeah, it can obviously tile a square.
And then the question remaining is there some k such that like k times 3n is possible, where k is not even? Like, is it possible that you could do a 9 by 9? I'm not immediately seeing the proof for that, but...
Yep. I mean, it's obvious that if n is not a multiple of 3, then you obviously can't tile it. If it's a multiple of 6, we've shown that you can tile it. But what if it's a 9 by 9? And that is a great question, and I'll leave that as a further exercise. And I'm gonna wait.
I might have a hunch. I maybe you can run with me with this, but
I will.
I think if you draw, my hypothesis here is that it's not going to be possible for any odd, like kn, like for any kn with k being odd.
Odd multiple.
Yeah. So do me a favor, draw like an L shape in the corner. Like there's two possibilities for how a piece can go in the corner. Right?
You want... Okay, I'll draw...
let's do both of them.
Okay. I'm going to give you this, and I'm going to give you this.
Yeah, exactly. So for the top one, there's only one possible way that a different colored L shape can be like snuck into that there. Yeah, exactly. And it's like that. And so you're forced to construct that same shape from earlier. Now for the bottom one, it's almost the same thing. The only issue is there's one different possibility where we can construct. Where I was trying to go with this is like, if we're forced to keep constructing those 2x3 blocks on the top, then like we can't use those to tile in what's it called? A 3 times an odd dimension block, right? So because 6 is even, and that has an odd number of cells. The only problem with this argument is, on the bottom one, there's like one way that you can wedge another L shape into that. No, sorry, there's multiple ways that you can wedge an L shape into it.
Yeah, there are, I believe, 2 ways. Yep, 2 ways. Because essentially, if you create a new corner, you can either fill it with
exactly.
or the other orientation.
Yes. Shucks, that might not go anywhere as easily as I thought it would. Well, okay, on the left side, you have to now make like the bottom, sort of like the cranny that is left is now forced.
Well, yeah, okay.
Yeah, so that's also forced. Let's just make those all green. Yeah, I don't know if I can take this anywhere.
I'm going to basically spoil the puzzle unless anyone wants to give it more time. Okay, I'm going to spoil the puzzle. Depending on... Yeah, okay, so this is a construction of a 9x9 tile.
Whoa.
Here.
So it's possible.
I put this in the and in the cover page.
I should have paid more attention.
I don't know. I'm not completely surprised that nobody picked up on that. But anyhow, I noticed this and I found this very amusing. I was okay, backstory, because I believe this is new for the person who's not people who are not previously in the Discord call, or like people who are viewing the recording. I was participating in HMMT, and we had like several teams, so we were like scheduled together. So I was with a bunch of math nerds, and we were looking at this problem specifically, of what things can you tile with what, and this is the puzzle which intrigued me, because I thought for a very long time that 9x9 wasn't possible, because obviously 3x3 isn't possible, and the rationale is basically exactly this. Like, you can't tell it at all. But yeah, for 9x9 it was possible, and you do it like this, and I'll admit that it kind of looks ugly. But I did manage to construct this while we were on a bus, which meant I just imagined this, but I did end up constructing this just without pen and paper, and I'm really proud of it. But yes, you can see this is essentially a 5x9, and with like a bunch of rectangles, which I've colored in red, which is like the ordinary bits, and some blue leftovers, like, which is just weird.
Right. So you're the first who ever did this?
I am definitely not the first. I am okay. So 2 reasons. There's a lot of buzzing. It's probably not just my problem, but like there's a lot of buzzing in here. Anyways, so I am definitely not the first person. First, this is a relatively easy to find construction. Second, I later found out that this is apparently a duplicate of a problem in ISL. I can attempt to search it up. It's an also problem about what shapes can you tile with trominos. I'm not sure if I can find it directly. But yes, there was a puzzle. There was like a problem in like something math Olympiad or something. I'm not really a heavy Olympiad person. About how about which rectangles you can fully tile with L tetrominos. Sorry, L trominos. And the result is that you can tile, because you can tile a 5x9, that allows to tile like odd stuff that is big enough, and then for even stuff you use the 2x3 module, and so that's how it works. Okay, so this is the construction for 9x9. Any updated hypotheses on what a L tromino can tile, specifically like for squares?
Multitube in the chat says every odd multiple of 3 from 9 upwards, which...
Yep, okay. Any explanation in mind? I mean, that is correct.
Well, I guess, I mean, you can just... you can't just naively tile it with 6x6 blocks, but you almost can, I feel like. You can tile it with 3x6 blocks, I believe, if I'm imagining that right.
Yeah, you can tile it by 3x6 blocks because you have 2x3 blocks, from which you can make a 6x3 block, which means that for any like for any 3n by 3n, you can always just extend this by 6, because you can go out here and then repeat this pattern over. So assuming that we have the same construction here, we can always just have this repeat, and then similarly for the other half. So I'm just not going to draw that. And that is the construction. So it's multiples of 3 except 3, because it just says nah. Okay, and that is all the trominos. And at this pace, we're going to be sailing past. Okay, we've gone monominos. I'm not actually sure what these are called. We've gone dominoes. We've gone trominos. Monominos seems like maybe it's mominos. Anyways, we've done mominos, dominoes, trominos. Next up, obviously, is tetrominos, and I'm also a huge Tetris fan. So I'm going to look at this problem. So, what do you all think the easiest tetromino would be to start with? 2x2, yeah. Any guesses? Yeah. A 2x2 would be able to cover any even by even square. Because we literally just have a 2x2 unit over here that we can repeat across multiple places, and that gives us the construction, which is really, really easy. Okay. Well, I guess upwards. There is one that is really obvious, but there are some other paths that we can take. So I don't think there's an obvious easiest one. Obviously, all 4n by 4n for the L tetromino. Interesting. Do you mean that 4n by 4n is sufficient, or do you mean that it's both sufficient and necessary? So just to be clear, L tetromino is this, and we're saying that L tetrominos can tile 4x4, 8x8, etc., but it can't tile let's say 6x6 or 10x10. I'm assuming that's not necessary, just sufficient. Yep. Okay. Which tetromino? Okay, I'm going to pick a tetromino then, and I'm going to pick the one which I think is the easiest to work with. I'm going to talk about the S or Z tetromino. It's funny. It's interesting if you try to analyze like what happens if you allow or don't allow flipping. in the end, I believe that none of I know for a fact that none of the results change for tetrominos, even if you consider like you don't allow flipping. But let's take the S/ZE piece and let's look at which squares can the S piece tile.
Well, you got to tuck one under the overhang there.
Yeah.
Well, I mean, even if we don't consider flips, then the other overhang is already unreachable.
Yeah.
But yeah, so you're screwed from the start. So I mean, I guess we have to assume that we're dealing with flips being legal. But in both of these cases, you'll just kind of run into the other corner.
Yeah,
like a ladder.
Yep. So the result for SNZ, which is why I said it's one of the easiest ones, is you'll eventually run into a corner because every piece you fill will end up just creating another cornered point in which you have to dedicate another S/Z to fill, and you'll eventually run into the corner. Or if you really want to, you can probably induction this, but I think it's obvious enough. So S/Z pieces unfortunately cannot tile any square. Okay. Now let's look at the other pieces. I mean, let's track our progress here. Right? I mean, okay. So monominos can tile all squares, so multiples of 1. Dominoes, multiples of 2. Right? So specifically, I'm going to say the O monomino is multiples of 1. The I domino is multiples of 2. The I tromino is multiples of 3. L tromino is multiples of 3, except 3. O tetromino is multiples of 2. S/Z is none. Or, I mean, I was gonna write multiples of 0 just to keep it like in the same pattern, but I guess I'll go with this. What else do we have left? Well, we have I pieces, we have T pieces, and we have L pieces.
Is an I just 4 in a row?
Yeah, I is just okay.
I guess that's going to be pretty.
This is a T. This is an I. This is an L.
I think I should just naively be 4 by multiples of 4.
Yep. Okay. We can start with any of T, I, and L. We already know that multiple of 4 is going to be a sufficient condition. Specifically, for the T piece, you can always tile it like this.
Oh, I forgot you could like twist it. Yeah, you could possibly have.
Yeah. With the I pieces, you can always do it like this, so that's really nice. With the L pieces, you can do it like this, and this is even like without flipping. So with T, I, and L, 4 by like multiple of 4 is a sufficient condition because we have these units. Yeah. As I very accurately draws it with ASCII art. Yes. The sufficient condition is the easy part. The harder part is the necessary. At this point, I feel like you can kind of just choose your favorite tetromino and see if you can get a result. Yeah, you can. Yeah. I didn't mention this. I felt like this implied, but yeah, I didn't mention this explicitly. You also rule out odd by odd because you don't have an even number of like divisible by 4 number of squares. But that means that you have to consider the cases for 4 for k plus 2, which is the only which is the only leftover cases. Yeah. So just to explicitly mention it, we know that multiples of 4 work, but maybe multiples of 2 work. Like, we don't know. I mean, I do, but
Me too. I wrote a proof about it a long time ago. Should I just tell you the answer for the T, or?
yeah, okay. You can go ahead with the explanation.
For the T, it's only 4x4. Like multiples of 2, like odd multiples of 2 doesn't work. And there's some kind of proof based on induction. It's a little bit complicated, so it's too long ago for me. I don't remember the proof. But yeah, it has to be a multiple of 4 for the T, and for the L, I don't remember.
Okay. I'm gonna say it is indeed true that. Okay, you continue. Never mind. But yes, it is true that TPs requires multiples of 4, but the proof is actually quite simple and doesn't involve induction at all. So remember how in our original motivation, right? The motivation was if I had like a checkerboard pattern like this. I'm gonna copy that over. If I have a checkerboard pattern, remove the 2 corners, then this can't be told with dominoes because the number of black and number of whites don't match. Here, it's a kind of similar case with the with the T tetromino, except it's kind of like a flipped condition. I'll leave the checkerboard here. There's answers in the comments, like answers in the chat, which I've already seen. But you can think about why this means that. I guess I'll take it to 6x6. Why 6x6 cannot be tiled with T or T. T tetrominos.
Okay, so you have 2 types of T tetrominos on the checkerboard. Some which are darker and some which are brighter. Basically, some of them have 3 dark fields and the other one has 3 white ones. So, and yeah, for the corners, we already know. I mean, the color of the corner dictates what the color of the tetromino has to be that fits in the corner. Right.
Kind of. It's not that complicated. Okay. I'll say
so it's
all
like
this.
okay.
Okay, I'll explain. So let's take.
I know. I think I got it.
Okay.
The number of black squares right now, if you count them, it is 3 times 6, so 18. That is not a multiple of 4 because the original size of the square is like not a multiple of 4. Yep, and that is a problem because we need the same amount of black T's and white T's, right? So we know that a black T has 3 black squares and a white T has 1 black square. So a pair of a black T and a white T should have 4 black squares. And if we like pair all of them, then the entire number of black squares must be a multiple of 4, and that's impossible.
Yep. I had a basically similar, but basically identical proof in mind. But yes, so basically that idea, because there's an equal number of black and white squares, and each T is either, so if you if you take this T like this, then it covers more black squares than white, and if you color it like this, it takes more white squares than black. But critically, it's either 3 black and 1 white, or 3 white and 1 black. And to have the blacks and whites cancel out, you need to have an equal number of black T's and white T's, basically. Or like, so you'd have to have, so basically each black T has to pair up with a white T such that their colors can cancel out. But each pair has 4 black squares and 4 white squares, whereas there's not a multiple of 4 squares total. Or there's not there's not a multiple of 4 total black squares or multiple of total of white squares. So for each pair, you have 4 black squares, and that will be impossible to cover the 18 black squares. My initial proof would be that since you're going to be using up 3 black squares or 1 black square every time, and you're going to have like an odd number of total or like, okay, let me just write this out. My idea is that since you have 36 total squares, and then you have, okay, what was I going to say? You have 36 total squares, of which 18 are black, 18 are white. So if I take the black minus white count, it's going to be 0. But each t, I see. Okay. Each t either contributes 2 more blacks or 2 more whites. So no matter what you do, the black minus white counter must always shift like in either direction by 2. And so after a total of 9 t's, which is an odd number, it can't return back to 0 because it started at 0. And I realized that if you know that there's a total of 9 t's, then you can end it right here, because you straight up cannot pair it together, because you have 9 total t's, and so there must be more black t's than white t's, or there must be more white t's than black t's, and that will mean that the colors won't be able to cancel out. Yeah, so that's I guess that's a more straightforward proof than either. Okay, so the t-piece is done. The t-piece is only multiples of 4. Now we're going to continue to the other cases of I and L.
Think I have a proof for the I.
Okay.
I claim the same fact that it is only doable for multiples of 4, and I think this works. So the idea is you're going to do another tiling pattern. It's not going to be checkerboard this time. What I have is like a larger checkerboard of size, like each checker is like 2 by 2. Yeah, like that. And then, yeah, exactly. So that would be like a 6 by 6 grid. Now you'll notice anywhere you place an eyepiece on this grid, it will always still take 2 dark squares and 2 light squares. So, however, if you count it up, this one has 4 more dark squares than light squares. So there is not going to be a way that you can possibly tile the whole grid.
Yep, and that is the same proof that I have in mind.
Sweet.
So this is actually, yeah. So you can only tile multiples of 4, because of actually a very similar argument to the one with the initial domino one, because with the initial domino, what you have is more black squares than white squares because you remove 2 white squares. But here you have more black squares than white squares because of the way that you tiled them, or because of the way that you colored them. And remarkably, no matter where you put this eyepiece, it will always span 2 black squares and 2 white squares. And therefore, it will be impossible to tile this square with eyepieces because you can't get the black and white difference. And that is the result for I. That leaves us with L or J. Pick your favorite letter. So what do we think about the result for L or J? So Sawdust in chat says, I suspect there are outlier cases for the L that allows all multiples of 2, the possibility for wonky cases, etc. Oh, I also wanted to point out that the eye tiling was like, I also got it from the video that was mentioned earlier. That I do remember that video and having watched it. So that was a nice video.
Is it the polymath video?
Yeah, the polymath.
He's in this Discord.
Yeah, I did remember that being mentioned.
I'm busy trying to tile one of these, but I'm not getting anywhere.
I will give a hint in like a couple of minutes.
I don't have a checkerboard that I can work this out on, so I'm going to be thinking about it as I'm talking about it. But it seems like actually for the L tetromino, there's something with the way that it has to like land in the corners that leaves on the edge a certain number of squares that must be covered. And maybe there's still wonky cases that are allowed no matter what, but
Okay, I will give as a hint that the result is indeed that with the space argument, it's very iffy, and I don't see a universe where it works out really nicely. And I'm gonna follow up with why I think that, like, I think soon, and by soon I mean a lot later. Probably not a lot later. But anyways, the result for L pieces is actually you can't tile all multiples of 4. Sorry, all multiples of 2. And the argument is a coloring argument, so I'll give you all more time to think about it. Are reflections allowed? It doesn't matter. Specifically, what I'm saying is, because if you look at this construction, even if you don't allow reflections, you can still tile multiples of 4. And I'll tell you that even if you do, even if you do allow reflections, you can't tile non-multiple of 4, multiple of 2s. So it's like for tetrominos, it doesn't really matter. Considering 4 colors on the board, I think if you tile it with 4 colors, depending on how you're thinking of tiling it, because I see 2 obvious ways of tiling it with like 4 colors, but depending on how you do it, it could work. You don't have to, though. Do I know if it's true in general or just for El Tetromino? I will be yeah, I will be very surprised if it's general. I don't immediately have a counterexample, but I feel like if you give me 10 minutes, I can cook up a counterexample. Way, if any of you all want any hints or just for me to review the solution, I'll be happy to. I just want to give you all time to think about this because I feel like this is findable in a way. This is like definitely solvable.
I was trying to think of like coloring things based on knight's moves, but I'm not sure.
Interesting. I'll get back to that idea later. Just to work, what is your idea? Color rows / columns the same. Interesting. Anyways, Zai, do you have a specific idea for what you mean by tiling by knights, or just like a general idea for?
I mean, if I'm only thinking about one, like not flipping, then the thing one like L should always cover some kind of knight's move between the two ends. And
Ah.
I had an idea, but then I didn't have an idea. So I was trying to color it. Yeah, basically what you're doing right now. Something like that.
Okay. I don't know if this works. I mean, this obviously doesn't work if we're considering reflections, or at least I feel like this shouldn't work. But let me think about what happens if we don't consider that. I don't know. How many of these are there?
Yeah, I think if you color like odd rows and even rows differently, or columns, I think you can do it very similar to the T argument.
Yeah, I mean, I know that that works, but I don't want to explore something that I know works. Let me look at this. Did I forget the color of this? I did. Okay, so I have 5 colors, which is interesting. Each L will tile 2 of the same color, and this is weird. So I can tile 2 of the same color and 2 other colors, but they can't be like blue and green, and they can't be like white and red. That's weird. I feel like there's a possibility in which you can like weirdly group these to have an argument that works. But anyways, returning to at least the other idea, you can indeed color the rows alternatingly, and you get this. This is also the solution that I had in mind, whereby wherever you put an L piece, it will either be 3 white, 1 black, or it must be 3 black, 1 white. So for instance, if I do it like this, you get that. If I do it like this, right, even if I consider flipping, you get 3 black, 1 white. And this thing works. I am curious about Pishelback's other thing which works. Or if it's the
Well,
same.
I have one. I think I've got one that works using a 4 coloring, where each L shape has none of one of them, one of 2 of them, and 2 of the last one. And then because you've got an even number of exactly 2, and you need to use exactly 9 L shapes, you're left with 2 out of the 4 with an odd number covered at the end, which doesn't work because you've got an even number of all of them, I think.
Okay. So yeah, this indeed also works because if you really think about it, it's just coloring, like it's just increasing more separation within the rows, which will end up working as well.
Yes,
so
it's basically the same thing. Yeah. Cool.
So if you do the coloring, like as Multitube says, color according to n mod m m what the fish m mod 2 m mod 2, then it does also work. Specifically because even if you just take mod 2 of one of the rows / columns, it works. So L's are also multiples of 4 exclusively. This is where we tread into pentominos, also known as I want to die. Because last week when I was trying to do this, I started looking. I was like, yeah, I'll go into this blind, and then I did a little bit of a run through with a friend. I was like, okay, I feel like pentominos should be easier. I realized they weren't. Did some research. They weren't. But we'll start with the simple ones, and specifically the ones which we know how to solve. I see typing in chat, but I guess I'll address it when it's out. Okay, so first, how do we list all of how do we list all of the pentominos? We start with the tetrominos. So I guess that's an O. that's an S, that's a T, and that's an I, and that's an L. And we try to add stuff onto them. And so with an O, wherever we add, we get a P. With an S, wherever we add, we either get a P, or we get an N, or we get an F. I still find it very amusing that they had to have names for all of these. Here, you can potentially get a T, potentially get a Y, potentially get an F, potentially get an X. Right? This you can potentially get a Y, potentially get an L, potentially get an I. I'll put it like this. The L, you can potentially get a T, potentially get an F, potentially get a Z, potentially get an L, potentially get a U, potentially get a P, potentially get a V as well, and potentially get an N, potentially get a Y. Okay, so these are all of the 12 pentominos, which again I still find it very fascinating that they have letter names for all of them.
Please elongate I by 1.
Oh gosh. Well, okay, we're gonna start with the easiest one, which this time is I.
Is that the easiest?
Let's look at I.
I don't think that's the easiest.
It's one of the easiest. Yeah, it's one of the easiest. Let's.
Well, I guess it's I guess it is just 5N. I want to just discard there's 4 of them here that I think we can just discard easily.
Yeah, I was gonna get to that. Let me, because I really want a way to organize these, so let's organize these by alphabetic. That's not. Okay, so here what do we have? We have, starting with the F pentomino, M pentomino, T pentomino, X pentomino. Where's my W? Oh gosh, okay. Yeah, I just forgot about W. Oh, here we go. P and Y Z. You can see that they really like the later letters. U L F T X V W and I. I'm just gonna, yeah, I is multiples of 5, because if it is a multiple of 5, then you don't have a multiple of 5 amount of squares, so it's clearly impossible. But if you do have a multiple of 5, then here's a construction, so that's a unit. Okay, and we're gonna go with the discarding. So.
All right, I choose to discard the X.
Yep, we're gonna.
You can never fit it into a corner.
Yeah, okay. So the easiest, most methodical way is to fit this into a corner, you can consider the bounding box. And the bounding box has to one of the corners has to be on the corner of the bounding box. And X has none of these, so X is discarded, so none. What else can we discard? You discard F. Okay, F, specifically, the only thing that's capable of being a corner is this. And if we attempt to chuck it into a corner, you'll find... Oh my god, I forgot that doesn't work. If you attempt to chuck it inside a corner, you'll find that you can't tie these remaining spaces. So F does not work, fails. And yeah, a lot of these just fail because of corners.
I think
for you. Yeah.
Sorry.
Okay, you can.
I was gonna say the T. I think the T fails because once again, there's only 2 that you can fit into the corner, and in both of those cases, there's a length 2 block.
So I'm just gonna speed run through these because this is not really fun. For the MPs, if you consider putting it on a corner, let me take a smaller stroke width. If you consider putting it on the corner, you'll have stuff that's left that you can only tile with another piece of the same thing, and you'll just get into repetition, and it eventually fails. Same thing if the corner is like the other side. So n also fails by n. N is none. Same thing for the u. If you let's start with t. Same thing for the t. The only thing that can go on a corner are these, which if they go on a corner, that means you have these two, and that fails. So that's impossible. So I'm just going to mark here t is none before I forget about it. We're also going to look at z. Same reason. Corner. Two remaining that you can't tile at all. Another one is going to be. We can also look at u. If you put u on a corner, then you have this space, which you can only tile with this. And then you have this corner, which is impossible to tile. So u is impossible to tile. So that's t, z, and u. Right. W is impossible to tile because one of the corners must be this. And so you have this, which is only possible to tile with this, which is only possible to tile with another repetition, and you have to go on and on and up. Okay, so these are all impossible. So I'm going to write here, t is none, u is none, z is none, w is none. Great. Which leaves us with these. Which leaves us with these three. These four. What else do
I think I'm assuming that one's the L, the one that. Well, wait, there's two things that look like an L here. That one, yeah, that one. I think I'm convinced that one's not possible, because there's two different ways that you can fill in the sort of inner crevice inside of the centerpiece in the bounding box. Yeah, there's two ways that you can reach that spot if it's in the corner, right? And it has to be in the corner with the corner piece in the corner, because if it's not, then you'll have exactly. So that's one option. There's a second option, which is to exactly. And
there are more scenarios though. This can go on the corner, but
right. That's what I was saying with if it's like that, then there's no way to reach that inner corner there. So that's not possible.
Yep. So this is just casework. Basically, if it's like this, then this has to be reached with this, and this is impossible to reach.
Yep.
If you go it like this and you take this path, because you have to reach this, you either reach it like this, in which case I believe you can only reach that with that, and then you can only reach.
Exactly. You can only reach that with
either this, but that's impossible. So you go down, and then this one also goes here, and this one is also forced to go here, and that's just impossible. And on the final case to the right, if it looks like this, with this being the corner, then where do we go? This has to be filled with either this going to the left, which is impossible, or going to the right, but then this is impossible. So this is impossible, and basically V is impossible. Basically V sucks. Now what? Okay, hold on a moment. I'm gonna deal with some. You all can hear me, right? My internet disconnected, and I'm gonna have to deal with some stuff.
Yep, we can hear you.
Okay, I am back. I'm back from fixing some internet issues.
Well, one fact that I've discovered, at least, is that the top two that you have there can definitely tile odd or even multiples of 5, like so multiples of 10.
Yeah. Okay. So we have here some easy results. If you have this, then you can take that, and if you have this, then you can take that, and this allows you. And this allows you to have a 2x5, which you can make, which you can eventually make into a 10x10 by just having 10 copies, and then you can make that into a 10k by 10k. So we're gonna write multiples of 10, multiples of 5, maybe, and then same thing with L. What do we think about Y? Okay. I am going to end the thinking here. I mean, I'm gonna take any conjectures, but I won't give too much more time to think because there isn't much easy progress here. Like, I don't believe there's any progress you can make within like a reasonable amount of time. So I'll be taking any hypotheses that anyone may have regarding these. And then afterwards, I'm going to show you the results which I've discovered online via searching. But yes.
I'm suspecting that they might be tileable for sufficiently large, even odd multiples of 5. I'm not sure which ones though, but maybe all of them.
I'm going to be taking. I'll take any hypotheses, even though I don't see any per se. Or do I? Hold. Okay. My VPN disconnected. Tileable. I guess Y has a corner problem. P and L are multiples of 10 because of normal checkerboard coloring. P and L are multiples of 10 because of normal checkerboard coloring is not true. Because originally what we had is what did we have? Yeah, okay. So originally what we had was if there are multiples of 2 but not 4. Okay, let me demonstrate. If it's a multiple of 2 but not 4, and then you decide to do a checkerboard pattern, so like this, you have the same number of black and white squares. And so if one of them covers like more black squares and one of them covers more white squares, it fails. The thing which doesn't hold on true is that if you try to extend it to 5 by 5, you begin with a different number of white and black cells, which throws you off. Which means that the result cannot hold. This is where it gets interesting. So I have actually cached these results because I knew I was going to get to them. They are, in fact, all tileable, ridiculously. They can tile all 5 multiples of 5 except 5. Holy shit. Wait, what? Wait, that was...
I think I might be a genius.
Wait, that was so quick. Holy.
Where's this?
Well, I mean, I guess it's a 10 by 10, so it's not as hard as a 15 by 15, but still. Like
yeah.
My first thought was that was a 15 by 10, but still, that was
my hypothesis was right.
Yeah.
Wow.
Oh.
That's cool.
Yeah. That's a 15 by 16 tiling, is it not? I'm looking at the Pentomino by multi-tube.
Oh, it is.
Yeah, I was like confused. That looks too simple. Okay.
Those tilings are crazy looking.
These tilings are crazy. Okay, let's look at, this is arguably the most sane one. This is the tiling for, okay, so because we have a 2x5, that means that we'll be able to get a 5x10, because 10 is a multiple of 2. So that means we'll be able to extend these by 10 at a time. So that's why we know that this can extend. And here it's similar, except this is just a straight up construction for 5x10. We'll get to that later. For P, it's straightforward to check that you can't have a 5x5 tiled for each of these pieces. And what you do is you create this insane shape, which works, and then you pat it around with a bunch of 2x5s to create a 15x15. And you can extend it. I feel like this is like, maybe you can discover it within the time frame. And this is L. Same thing, but with a bunch more pieces, like with a bunch more patternless pieces. I also have to say, I'm not necessarily certain that these are the most elegant ones. I'm pretty sure they are, but I don't know. These are results of searching online. This is 15x15 with construction by L. I remember I did ask. Okay, so because I was typing like, which squares can you tile with? Okay, can you tile a 15x15 square with L pentominos? And you know how Google has this like automatic thing? I could have sworn it told me something about 3-color. Yeah, and it's just like something bullshit about just random colorings. So
Well, there it is again. It just
look.
lied to you, didn't it? If you scroll up.
Yeah. Well, yeah, but like exactly this. It was like, but it was like specifically in like, it specifically gave me a reason why. So I was trying to understand it. But I realized that was bullshit.
Yeah.
But yeah, I would be really surprised if I can find it, because I remember that it took me some decent amount of yeah, polyomino tilings. I believe this would be correct. But yes, yeah, that's the side which I will show. But yes, now on to the crazy stuff. There's a 5x10 tiling when using Y pieces. And oh, by the way, all of these use flips. So, and I'm pretty sure the rotating wouldn't be possible. I haven't explored it. I'm probably going to explore it like right after I finish talking.
Well, actually, well, I don't know if you have time, but
I mean, like,
I think I have a way that you could disprove the P's working.
No, I mean right after I finish this section.
Oh,
of talking.
okay, yeah. Sorry, go ahead.
I have not looked into it at all, actually, which I feel ashamed. Anyways, this is a 5x10 tiling with Y pieces, and so you can use that to make a 10x10 Y. That tiling is gorgeous. Yeah, I feel like this is also I actually just read this is also like a symmetric kind of construction, which makes it extra nice. And you have this monstrosity. I don't even want to. What? Like I was like doing this. I was like, okay, I can maybe like color this together. But then after a while, I just give up. I can certainly still try. Let's see. These pair up together nicely. These pair up together nicely. These pair up together nicely. But it's just that this is so much like just more non-standard than like all of the other ones. It was like for all of these I could get these relatively sane tilings. This is just a 15x15 monstrosity. And again, by the same argument, because I have this 5x10, I can extend this to make like basically bigger and better monstrosities. Okay, and all of these are thanks to polyomino tilings. As you can see, I looked into a lot of this actually shows you what you can tile with what pieces. So if you look at like if you're just interested in a random, I don't know, monomino plus heptomino, because why not? Then you can show all of the information that other people has. So like this, it's like reptiles, etc. And so, for instance, if you wanted to look at the result with that L piece, then you can show, you can get this and a lot of stuff. Okay. So I will be sending this in case anyone wants to look at this. Oh,
So wait,
okay.
when you select two things there, what is it doing? Are you talking about like it's asking about what's possible if you have either of them available?
I think it's both. Like, so you have this.
I see. Gotcha.
So yeah, that's smallest rectangle, smallest square. I think it also assumes that you have to use both of them because otherwise that'd be 4x4.
What the heck is that 70-omino that they have listed?
Oh,
And why does
I
that
think
exist?
okay. This is a specific tile set with the 70 omino, 66 omino, and 20 omino. I think apparently. It's just
Why?
it's just apparently that exists. I don't exactly know how it works. But yes, they can apparently tile something, and I believe that it's probably there because it's used in the construction of something, but I'm not really sure. But yeah, this is just a fantastic resource. Anyways, getting back to the original, because I remember somebody said something about disproving 4K plus 2 when you have like L's, like L tetrominos. I feel like this makes me lean into thinking that proof approach doesn't quite work. So that's specifically why. Okay. So I'll first everything that I've prepared is done. So I'll start exploring random shit that I don't know. And I'll start with what if you don't allow reflections? In which case I think you get into corner problems. Okay, yeah, you do get into corner problems because if you look at one of the corners, which is like this, does it?
I don't see a corner problem there.
Oh, I don't see one either. Solution. Okay, yeah. What else? What if I think about the ways it tiles? Okay, you know what? Do I want to even try this problem? Because I feel like there just exists a super stupid tiling.
Whether you do or don't, I'm gonna write a solver after this to try and find them.
I mean, I am aware that other people have wrote solvers, but that's not the same because it's not like
better.
this result matters.
Solvers are fun because you can optimize them, and I don't know. I'm kidding, but I want to try anyway.
Yeah, I mean, sure, go ahead.
Yeah, like that's not immediately looking unfeasible.
Just gonna try random stuff.
That seems like you're in a wait. That looks like you're kind of in a bind though. You can never fill that bottom left corner now.
Yeah. Oof, that's.
Wait, but you can still make the 5x2 block. In case that wasn't obvious, I mean that was probably obvious.
You mean like here?
Yeah.
Yeah, I was. Yeah. Anyway, that what we're trying to do is do this, but without flipping the pieces, or like without reflection, like only rotation.
What? Oh, the thing above, right. Sorry.
Yeah. So
I was not.
I'll try to see if, because you can still get the 2x5, so you can still get 10k to by, like you can still get multiples of 10 without without reflection, but can you get 15 by 15? And I don't know if I want to try. Okay, how feasible is this if I go into like What's the probability of me frauding myself? Okay, I'll try more manual and see if I discover anything, but I strongly think I won't. It's just like, it's so absurd. Why would this even work? But also, like, why would this not? I mean, because I would be really surprised if there was just like an actual legit proof. I'm just more so like, because like there might be some tiling which can prove that it's impossible, but at the same time that feels really weird. Like it's just not something that I feel like should exist. Oh, is this just that's just unfillable. Well, I guess I can. What can I do about this?
I mean, if we just do a checkerboard, then a P should always cover like 3 blacks and 2 whites, or 3 whites and 2 blacks, right?
Right, yeah, but you start with more blacks than whites. Like, so supposing you have a 15 by 15.
I mean, keep in mind, whatever proof you do here has to make use of the fact that it already worked on the case where like reflections are legal.
So, like, it has to differentiate between reflection and non-reflection.
Yeah.
That's actually... This is really hard in one direction. This is, like, much harder in one direction than it is in, like, in the other.
How so? Like, why not just fill in? Like, I'm not sure what the problem is. Like, try and you see here. Just put your mouse somewhere, and I'll like direct you to where I think you might want to put something. Okay. Actually, go right. Yeah, go right a little bit. Maybe like four cells. Yeah, that up to the thing. Yeah, up 1 and 2 to the right. Like, I think you can fill in a nice box there. Yeah, that one, and then the cell 1 to the right of it. No, not up there.
Oh,
yeah,
yes.
yeah. I think if you do that, then
I know, but like I'm concerned with this part because right now this part is impossible.
trust me. Just
Because-
fill in the next one that's now forced, and then that one I'm pretty sure will fall into place if I'm doing this right in my head. So now flip put one more in there, but it's like a P facing rightward. Oh wait, shoot, we don't have reflections. Crap. Never mind.
We don't have reflection, and that's...
I've been
like, I think...
Yep.
Just straight up screwed.
I've been doing this in my head as though we did.
I feel like the night checkerboard might help this time. Interesting.
Yeah, I'm trying it right now because the night trick, if you remember last time, it gave us exactly 5 colors, right? I feel like there's something there.
Also feel like that's possible. Interesting, because these 5 by like these that pattern repeats every like 5.
The kind of annoying thing here though is that like, oh yeah, because you do have 2 pieces that are separated by a knight's move in this case. However, because like the knight's grid is like chiral, and so is the piece, you might just have to choose the right direction of knight tiling, and then it works.
Yeah. Huh?
That seems workable.
I don't know. I don't see an obvious way of it working. But I don't know.
I'm gonna try it.
It's weird. If we like, can I share this in chat?
Okay.
If we
sure.
do this,
That, with my current orientation of P, I'm assuming.
yes, with your current orientation, like the Q shape, then the Q covers every color exactly once.
Yeah, I see.
And I feel like there's something there. Just an idea.
Yeah.
But it immediately, just... Look, it's okay. Do I want to... Do I want to potentially front myself? What would be the best way to cut this? I would. I'll have to start at the corner. Do I want to detect? Yeah, I don't know what the easiest way to do it here is. Because also, I've never coded something remotely like that. Surely I have to try, though. I mean, in case anyone doesn't know, you're free to leave at any time. I'm gonna attempt to code this, and I'll regret this. I shall.
I am having flashbacks.
I will call this unrefrauding. In case you haven't figured out, my naming conventions are out of the window. Bad. Okay. N equals 15. So we're N equals 15. So we're dealing with a. Oh my gosh! I just wanted to type this because I've been using Discord way too much. M by N grid. Surely I can just hard code this. Yeah, I'll hard code this.
You know, you can do 7 times 15, right?
What do you mean?
With this shape, you can do like a rectangle of 7 times 15.
Wait, how?
Looking at it in some wait, I'll try to take a screenshot.
Okay, do try that. I'm gonna continue with this a programming approach because I've had that's surely gonna be beneficial at some point. That's
just looking at some old paper that I remembered. Some high school student wrote this to complete high school in Switzerland in German.
Interesting new countries to write fascinating high school papers on. Orientations. We're gonna have. How do I want to encode this? Do I really want to use a bitmap? Can I not use a bitmap? I feel like I have to use a bitmap to get this to run like even sufficiently reasonably fast.
You're trying to do a 15 by 15, right?
Yeah.
Yeah,
like I don't
use a
know
bitmap.
Yeah, I don't know how to find.
I don't know how crazy you want to get about this, but there's a way that you can do like you can use SIMD to like do like a pack like a 64-bit integers and like make a 16 by 16 box. But that's kind of crazy.
Well, I mean, I'm in Python, so I'm not worrying about like overflow. Oh, 7 by 15. Yeah, but that has flipping.
Okay.
Wait, no, that doesn't. Like, oh, does it have
the
flipping?
the two bottom?
Oh yeah, you're right.
So that's not what I want. 37. That's not what I want. Great, gotta love this perfectly readable code.
What are you writing?
These are the orientations for the piece. I guess here.
What's your notation?
These are just the bitmaps by rows.
What do you mean by that?
Specifically, these are the 1 1 and then 1 0 1 1 1, and that would be 0 0 1 1 1 1 1. I think I see problem.
Well, I guess if you're in Python, you could just do a 16 by 16 bit board. It's not going to be fast, but it would at least work.
No, I'm like trying to think about how do I want to encode this. I think I'll just hard code this somewhere else.
Oh, I know. I'm telling you how to encode it. I mean, it would work. I don't.
Yeah.
It wouldn't be. It wouldn't be.
TwoSwap is just saying that you don't like pre-calculate those numbers here. You just do a bit board, and then every iteration you just like put one there, go right by one, put one, go right by one, put one. That to make 3 blocks, and then like just
Oh,
do
so
2 blocks below that.
So if I have like something like this, I'll be like pasting this and duplicating it on multiple times to see like which places remain empty.
It's
No,
like
that's
a
all.
recursive function. In each step, the function is gonna put one block in the leftmost corner of the. I mean, if you look at all the unfilled blocks, the recursive function is gonna look at the top leftmost unfilled block, and try 4 different iterations of the Q block. And
Okay,
for
yeah.
each iteration, it's going to put one block there, and then it's going to recursive call back on itself, and then put the next block. And then if everything ends, then it's going to try the next rotation, and so on 4 times.
Okay. Right. Okay. So I want to put it somewhere in my recursive function. Good. So not here.
And yeah, so the representation that I'm suggesting is, instead of doing that, you just have, like, if you just have each like bit, like this is a 16 by 16 grid that you're working in, or a 15 by 15 because it's Python. We don't care about the integer bounds. You can just call you can call a P shape, like in binary, 1 1 1, then 12 zeros, then 1 1, and then zeros until the rest of the 15 by 15 board is filled.
Yeah, I'm just worrying about because I was like doing this orientation because I know that if I do that orientation, I can calculate to get that bitmap and hopefully get it to be better-ish.
Wait, what do you mean?
But I was wondering about how I would make sure that P's don't overflow. In which case, I think I'll just add a border around.
Well, I mean, you can, but I mean, if you do the bitboard approach, then you can just check that the number is smaller than 2 to the 15 by 15 in order to check if it's in bounds. And that
I'm just worried that if I put something here, it's gonna allow me to put it, and then that's
no, it wouldn't, because you like if the thing. Oh yeah, I do see what you mean. But what you can you can just put it in an envelope of 16 by 16, and then
So it's like that does work. So I do see that now. So I'm gonna code that, which.
And then if you really want to get fancy, you can transfer it over to like some C and SIMD approach.
Yeah, not doing that.
Well, I mean, but at least with this approach, it like easily extends, is what I mean.
Yeah. Okay. So I'll need my grid. My grid will be whatever. I'll just use a for loop. I think for loop is probably best for this. Is this a thing? Surely.
It is in C. I don't know about Python.
I mean, it's not giving me errors, so I'm assuming it is. I have like seen this like I think once, so I like this might be a thing. I want. I don't care about efficiency. This is probably gonna get optimized anyways. Is it 2 to the 15 minus 1? Right. So that's gonna give me 15 once, and I bit shift 16 every time. Should that just deal with all of my issues? It seems so. I'm still really worried about messed up things that can happen, but I think this works.
Wait, what's your question? Grid shifts. What are you doing there?
I am making a grid
Yeah.
out of a 16 by 16 area. So
Oh, you're just
this
clearing out all of the. You're just clearing out the 15 by 15 top left corner. Is that what you're doing?
Yeah, I guess it's the bottom right. Depending on how you want to represent it.
Sure. Okay. But
I'll
wait,
guess
2 to
that.
the 15 minus 1. I'm not sure what you're. That doesn't work, right? Unless I'm misunderstanding. I'm pretty sure you're like that's.
I'm creating a row of like 15 cells, and then
shift
just shifting that
left.
up.
Okay. Yeah.
And then-
Yeah. Grid plus equals. Is that right?
One way to test out.
Yeah.
Because I mean, I'm gonna need this anyways, unless I somehow manage to not write a bug, which.
Yep.
Grid. I. 15 times I plus j mod 2. Okay. And I'll print that. And I'll print that. And hopefully this works. Okay, cannot fit int into an index sized integer. Oh, is it that?
Whoa,
Okay,
nice.
this is what I want. This is what I want. Obviously that's a bad mistake. I also wanted it to go from left to right reading them. I guess least significant digit being top left is fine to work with. Yeah, I'll just okay. Right. So I have this. Now what I want to do is I probably want to start with the least significant bit. I'll start with the least significant bit. What's I've forgotten because I don't write bitmaps a lot. What's the best way to get like least significant bit?
The least significant bit.
And with 1, and then check if it's 1 or not 0.
Something
Yeah,
about
that
X
gives
and
you that gives you it, but yeah, not the position.
Yeah. No.
not.
Oh, you want the
Yeah, I don't-
position of them, I see.
Yeah.
I don't need position, but is this what works?
Well, you could just shift it left by 1, and then check where there's like.
Also, it's not tilde. It's supposed to be minus, I think. X and minus X.
Probably. I
Yeah.
was gonna like check it. Probably just make
Wait,
sure that
what
it
is
works.
that doing?
Least significant digit of the the last one that appears.
Is that
but like
but how does that work? X and minus X. Like there's some twos complement stuff going on.
yeah.
Yep. Minus X is tilde X plus 1. So normally, if
oh,
you do
yeah,
X
yeah, yeah,
and
yeah, yeah.
tilde X, everything's gonna be canceled out. But
That's
yeah,
cool.
you added 1. Yep.
I was gonna say like left shift by 1 and then like look at the intersection between them, but yeah, that's even cleaner.
Like I remember something like this existed, so I was just like, yeah, I should check for that. SD. Now what I need to do, I need to check if all of these are within pattern. It's just whether the pattern is within the grid. That works. Okay. I may as well check what's the behavior with this. Good. Possible grid. Okay. I'm gonna have to make a cache anyways, but let's deal with. I may as well deal with that now. This is gonna be a Boolean value. Do I want this to be a Boolean value? Do I really want this to be a Boolean value?
Sorry, why are you doing the cache?
Doing the cache just so it might get slightly faster with duplicate grids.
No,
like
but
probably
you'll never hit duplicate grids.
What?
You'll necessarily not hit a duplicate grid. Each search is unique because you'll.
Yeah, if you're going for the method I said earlier, like 4 rotations, trying every placement, then you'll never get a duplicate. You need to go a dynamic programming approach, completely different approach to ever get a cache something.
Really?
Something.
Yeah.
Really? I was thinking like maybe like there's some setup in which after you place a certain amount of pieces, the space you've covered becomes the same.
Well, I mean, no, that couldn't happen. I mean, you do still have to, if you really wanted to, you could concern yourself with like symmetry according to like D4, like the group D4, like.
I mean,
flips
I'm gonna
of the
start
square.
tiling from the top left, so I don't think D4 is occurring like anytime.
Right. Exactly. Yeah. Exactly. So.
But I feel like surely there must be like some sort of case where like
no, because like
way...
you're filling each corner uniquely. Like.
Well, I mean, but like each corner has multiple choices, and sometimes I might run into duplicates. Like I'm not sure if it will happen.
I mean, I don't have a proof for you, but that doesn't seem possible. Like.
Okay, I will. Then I'll do this later.
Like you could imagine checking equality by tracing back along the
Okay. From functools and yeah, probably a good idea. I always just write a cache myself. But,
okay, here's a quick proof that wouldn't be an issue. So suppose you have 2 grids that are the same, and like they're not necessarily full, but like they're the same grid, which means you reach them both via different paths through recursion, but they look the same. So you can sort of imagine tracing the recursive algorithm through both of them. They both started in the top left corner. Then they would have had to choose the next possible thing. I'm not sure exactly how to phrase this.
I have a construction for how an instance of how it might occur. It's just not very probable. So it's like, yeah, okay.
No. But it's not possible. It's not possible because like.
Surely, if I have like this, then I can get the same thing just like this rotated 90 degrees. Like, surely there's nothing preventing me from getting both of these.
What do you mean by get?
Like, like my recursive algorithm can decide to place this here.
Oh, you mean the entire envelope as opposed to the actual tiling pattern? Yes. Sorry, I thought you were saying yeah. Okay.
Yeah.
Yes. In that case, yes, I agree with you.
Yeah. So I was like, I'm obviously like going to be caching the bit.
Yeah. Sorry. Yes. That totally makes sense. Never mind.
But I was wondering about whether, but I still think it's an interesting thing. Is it even worth it to consider?
Yeah, I mean, it's definitely possible that you just run this and it just immediately finds something. So I would maybe save it for later.
Okay, we'll do that later then. L equals grid. L equals LSB of grid. That's probably gonna be LSB, but whatever. FL is 0, return true. Placement given some X. I'll probably rename this to X. What are the possible placements?
Wait, sorry if I'm being slow here, but what does your LSD do again? It gives you.
Oh,
won't this always return 1?
No. So like, if you give it like 2 and -2, then.
Oh, it doesn't give you the index. It gives you the. It just gives you the mask highlighted. Okay, sorry. Never mind. I'm back with you. Never mind.
Placement. Return. Right, I guess this could just be x times. One. It's just gonna be a bunch of zeros. Oh my god. Oh my gosh. That's 15. So if I were to look at it in my current orientation, I mean, I don't even care about the orientation because it's like once it goes like it's not gonna matter anyways. 1 1. That's a 1. That's a 1 1, right? 1 1. It's gonna be 1 1, and then down like a full row. But that's
Aren't
a
you
1
missing
1
a
1.
0?
Like missing a 0 where? Like
before the in the middle, like with all the other zeros. Like you have 15 things in the same row, and there's like 3 ones that.
Oh, right, because
but-
I have 6.
Right. Well, no, but well, yeah, you would need another 0 there, and then another 0 after the. I think you need 2 more zeros, right?
I am. Okay, how do I? I'm trying to like. So this would be. I'm taking 1 and then 1. Holy.
Yeah.
And then I'm gapping. I'm completing this 16.
Right.
So this would.
So that would all be zeros, and then you
and
have 3
this-
ones. Oh,
So
you're doing it
I'm-
in the top right. I see.
Okay. And similarly, I'll be having 1 1 1 complete the entire 16, and then 1 1.
Okay.
Right.
Yeah. I think I think that works.
And then I'll be having that. In which case I'll be having 1 1 complete the 16, and then 1 1 and complete the 16, and then gap 1. And then I'll have one gap, and then finish the row kind of, and then 1 1, and then 1 1. So these are the placements, and multiply by x. Yeah, whatever. This is so not going to be the best way to do it, but whatever. Rectangles are tileable with P. Pentominoes with. Oh, okay. To answer Restaurant Gamer's question in the chat, which rectangles are tileable with P pentominoes without reflection? The result for P pentominoes with reflection is all multiples of 5 except 50. All multiples of 5 except 5 itself, and for without reflection, we know that multiples of 10 are possible. Obviously, non-multiples of 5 are impossible. So we're just looking at the other cases. 5 is obviously impossible, so we're looking at 15, and we're trying to make a program. If x is equal to 0, return true. Otherwise, for p in placement, I guess I'll call this placements. If contains, what did I call it? Oh, within grid pattern being P. If possible, grid minus P, return true, return false. Okay, what am I missing here potentially? For P within placements X, if within grid P, if possible, if it's within, and I can take that away, and it's possible that I can have it. Otherwise, return false. Also realize that's such a stupid. We love constants that never appear. using. I'm seeing a block of text by multi2, but I'm assuming it doesn't go anywhere. I'm unsure. This is okay. Grid. Print possible grid. If this runs within 5 seconds, I'll be pleasantly surprised. What? Okay. Pprint grid. Oh, that's a lot of cases. Holy shit. So, okay. I'm going to cut it off after some. Oh. Ah. I'm gonna do this because I don't care.
I think I got a code working. I
Oh.
think I could help.
You can just do yours. I mean, my code returned false, but I'm just not sure if it's just bad.
Yeah, I would be surprised if it finished that entire like.
Look at my absolutely befuddling code. I just don't want to deal with. What do you mean? Oh, of course. I just don't want to deal with global variables by subtly introducing them. Okay, so it's trying to make these. I mean, obviously, preferably, I would want to take care of these right away, but that feels like hard to construct, like hard to prove. Okay, Zai, you said you had code, or like you have what?
Need to debug.
Okay. Okay, I'm gonna throw away this spaghetti. I'm gonna see if what's a better way to see if this code is working.
By working, do you mean like exploring the entire recursive tree?
Yeah.
I don't
right now
believe
it's
for a
like-
second that that's completing the entire.
Yeah, but like, how do I even begin to debug this? Because
Well, I mean, maybe just get some statistics on like.
I've forgotten how the library works. It's not that.
What's that?
Thing which visualizes how many times each line runs, basically.
Oh, that's cool.
I'm confirming that.
Are there any squares? Are there any squares we do know you can do with this 5? What's it called? Pentomino
Multiples.
without rotations.
Multiples of 10.
Multiples of 10. Right.
I'm also
yeah,
gonna be going to ChatGPT very soon. For just visualization stuff.
Are there any odd sizes we know you can do, or does it seem none?
What?
Are there any odd size squares that we know you can
That's what we're trying to figure out.
No.
Yeah, we don't know any, and it looks like probably not 15. 5 is obviously impossible. This is.
Why is 5 impossible?
Nothing about this seems extremely suspicious.
Wow, that's. Wait, is it saying that it got called 2 million times? It's faster than I thought.
Yeah, that's the number of times it got called.
You said 5 by 5 is not possible. Why was that?
Because I checked possibilities. It's just
It's
not possible.
well, it's already known to not be possible even when you include symmetries. So
Yeah.
Right. But that's
True.
just, is that just by, there's not like a nice proof of that, it's just people have checked and it's not possible.
Yeah.
seems like it.
Right.
Yeah. Okay, I'm gonna tell GBD to allow me to.
Did you print out your pieces themselves?
Yeah, I mean, I printed out the resulting grid, which is basically that. I can do that again. Oh my
What is it?
God,
What do you mean by
what-
resulting grid?
Like, because I'm taking away pieces from the grid, so I'm just like the grid, like the new grid without the pieces. But that's basically the same thing.
Wait, sorry. Is that what you're doing right now? No, but what I meant
Yeah,
is like I want to see the actual definitions of the pieces and see that it matches the shape that we expect.
Oh, these are there. You can get that.
Yeah, but I mean, like, can we print them and look at the shape?
Let's see. Okay, I guess.
I mean, that seems like an easy place for a bug to hide. So, I mean, one way that we could easily debug this is, increase the size of that by 4 by just adding the flips, and we should see true.
Oh, okay. That does make sense.
Yeah, but I also am very dubious of my own ability at judging whether these are correctly written or not. So,
I would just be flipping all of these. That. I'm doing rotation by 180 degrees.
Yeah, that's why I think you should print them.
But no, I was like, when I was generating the flips. You know what? Let's do that first. Placements. Yeah, placements. That. Okay, I mean, clearly. I mean, that's not a bug necessarily, but
I missed it. Did
yeah,
it work? I mean, I guess so.
I'm assuming this is working because
Can you just
in reality this will be filtered as not able to be placed.
Yeah, maybe just make that like 8 times, or
Yeah.
I don't know, like 2 to the 17th or something. I don't know.
This, that, which works. Yep, works.
Yeah. Yes.
And right. Actually, yeah, good suggestion about testing that. How do I wanna do this? 1 1 1 1, a bunch of stuff, and then 1 1 1. So I can instead make this 1 1 1, a bunch of stuff, and then 0 1 1. 1 1 1, a bunch of stuff, and then 0 1 1. Okay, that's flipped. So what I'm doing is then flip from top to bottom. Okay. So that would be 1 1, and then 0, and then a bunch of 1s, and then a 1. Okay. And that would be flip the top from top to bottom, and that would be 1 0, and then 1 1. Okay. And then that would be 1 1, and then 1 0. So that would be 1. I mean, obviously, going to be testing that. And it should, yeah, that, and that. Should be. Oh no, that does not work. That's one of these is a duplicate. Yeah,
I have bad news.
Okay,
I have debugged the code. I think it's working fine now. And my code cannot handle the case of size 12, which means, I wanted it to say I cannot fill 12 by 12 grid with the 5 Pentomino. And the 12 thing, I put in 12 and it's not giving me an answer for a minute. So there's no way this works for 15.
Okay.
Well, yeah, but it's easy to find if there is an answer. Like if there's, or well, it might be easy to find if there is an answer.
I mean, but I'm also
That's
finding that there's no
true.
answer. So I'm also finding that there's no answer, so that's not an explanation. But
Yep,
I would
the
like
15 case is not, giving me an answer right away either.
I would like to see
So-
your Zai, if you can send that.
Right.
I mean,
Okay,
it's true,
I'll.
right?
How is that running that fast?
I have no idea.
Can you print it?
I have no
Can
idea.
we print the, what's it called? The output?
Not kind of, yeah.
I'm
I
wondering
guess
if,
kind of.
like if we can like color things along the way somehow.
I guess you can look at it by what? Oh, that's just okay, yeah, that's gonna be how would I do that?
I mean, you could just like, I don't know, like at the end, like when you traverse back up the recursive stack, you could just print things.
Oh yeah, true. If the okay, that's probably a good time to introduce a wrapper.
That's kind of insane, though. I can't believe it. That seems to imply that it's actually functioning. I don't know how they.
Oh.
How I mean, I imagine there must be some kind of I forget the technical term for it, but like where Python identifies that something here can be like rewritten in some kind of lower level language or something.
Yeah,
Because I can't imagine that this is just actually executing in plain Python that fast.
Wait, I thought it was bugged, but now I believe it's not bugged. And I think maybe this definitely tells me that it's impossible to do 15 by 15. There's still a chance that I have made a mistake, but I think it works, so I'm gonna share it.
Y'all can
How
share.
would I share this? Where should I? Do I just copy it and paste it on
Can you
Discord?
copy the code? I'm just mainly interested in the code.
Yep.
When I said that
But
about
anyways.
the recursive stack thing, is that what you're showing here?
Yeah.
Maybe we could just like
So I didn't implement the part where you wait. It says my message is too long. I've hit the 2,000 character count limit. Get nitro.
You can send it as a TXT, or you can just drag the file over, or if you
Right.
this. But yes, I think this works. Okay, the way you can view this is you can start with this, and then you can see pieces subtracted if you scroll up, and I'm pretty sure this works.
Cool.
I'm gonna be sending this code. This is like within Nitro. Holy shit.
I wonder if we should be able to rather easily extend this to the other two shapes, right?
Yeah. That is good. There is no shot this works for 25, right?
Well, try it. I mean, maybe it'll just find one right away.
26, 25.
I don't think it works for 25. Yep. It doesn't work for 25. At least according to me.
I mean, if it works, I'll be so happy, but surely not. Like that's way too insane. Underscore here, underscore here, underscore here. I'm just adding 10, adding 10 bits to everything I see. There's a non-zero chance I just forget to change something obvious, but whatever. Possible grid. Yep, no, it's not running. What?
Whoa, I found one.
What?
Hell yeah.
No. No, this is with reflect.
Oh. Oh,
With
okay.
reflection. But still, that's like super fast. That's like way faster than it should be.
I was expecting it would be instant. For, like, if there is one.
Yeah, probably true. I'm just gonna leave this running. There's no shot this finishes in time, surely. Do y'all might preferably put it in spoilers? I mean, I'm liking doing code, so. And also, like, to what extent your solution is. Okay, so we look at. Okay, I believe we don't need any more of that. Still waiting on Zeisco, by the way.
Commenting on it.
Oh, I guess you don't. Well, I guess you can send an uncommented version first, but.
Oh yeah.
P. That's P. L. Which okay, I'll send this as my primary standard for L. This exact problem being with P specifically, or like with the other pentominos as well. Because if it is with P specifically, I'd be interested to just know a solution, because that allows me to like maybe tackle the other problems. With P and L flips, okay. Share but spoiler. It's gonna be a. Ooh, that's gonna. Ugh. 1 1 0 0 0 0. I guess I can just do a left to right. Okay, 1 1 1 1. And then the full shenanigans, the full 16, and then 1. Rotating it. It's just gonna read this backwards. Yeah, I assume that was just a link. 1 0 0 0. 1. Wait. Okay, that's yeah, okay. That's one line. Holy shit, we have 3 lines. 1 2 3, and then 4. And that's just going to be reverse, so 1 1, and then
I'm going to send the file in the chat.
Okay, 1 2 3. Oh, that's just a debug. Okay. Boom, 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 boom. Yep. Okay. False. I mean, okay. I don't know if I want to trust it though. Undian fraud. Okay. Holy shit for kilobytes. I'm just gonna name it fraud. No, wait, same. Oh, it's a size 25?
Yep. So what you're seeing is it succeeded in placing 24, that's the first line, before it found some impossible square to fill, starting from the top left.
Okay.
And the numbers below, so I just wrote it like that to reconstruct this. If you look at it, yeah, the comment. The number denotes which rotation has been placed at that point. So I haven't wrote the code to reconstruct it yet, but we can reconstruct it like manually because the code decided to put the rotation 1 case at the top left. So yeah, if we place that, then the next empty space is gonna be like I don't know. I didn't make the reconstructing part. Well, I can do that later. But I think if you put in like size equals 10, then it correctly says that you can place all 20 pentominos in the grid. So it works for size 10 and 20.
Okay, check empty shapes, all shapes. Heck. Oh, are these intervals?
So, wait, could you like increase the width of your window a little bit? Is it possible to like shrink the size of the font? Because I tried to,
Font size. I usually deal with super large font sizes, so that's why.
Yep. So on the top, I just define the bitboard, which is B, and then I have a simple get and set function. Final, you can just ignore that part. Get and set function, and then
Get and
below,
set. I see. Okay.
And the check is gonna check the first empty cell. So
Right.
that's like, if not get B, that's how you check the first empty cell. Then you're gonna try all 4 shapes, and the results are gonna be the result from putting in the 4 rotations. You're just gonna find out which rotation resulted in the maximum number of pentominos, and then I just do something with that. Yep.
Okay. So this is trying to maximize which I guess makes sense. So because mine would just not not care about the number, maximizing the number. It would just end if there isn't one.
And all the things below are just like, I didn't have time, so I just copy and paste it. I made one and then copy and paste it. So each of the functions check for one kind of pentomino. I denoted it with the little circles on the top. Just check if we can place that pentomino in the current position, in the ijth position, and place it, and do that.
Check. And so check would be the number of stuff you can place. Changing 25 would work, I'm assuming?
Yes.
And so this would be possible with 10. Okay. So and 20 meters possible.
Yep.
Okay. And how would I interpret this? 2 would mean
I think I didn't make it correctly, so you can just ignore that part.
I kind of see how it works ish.
I could like fix it so that it shows how to place things, but yeah.
I see how to read this. If it's a 2, I place a 2 down, and it overrides any numbers that it has just because the code hasn't handled it. And okay.
Yep.
Okay, and that just repeats. Okay, and do I dare look at the 15 case? It puts 14 of these.
Yeah, so 14, and then it found something impossible.
Okay. Oh gosh. Okay, yeah, I can't read this. Yeah, I cannot read this. Well, okay, I'm gonna check out the math link, hoping that it contains something. And also, I'm gonna P Pentomino be proven that a 5 by n, but only by considering for 10 by n showing it this way, then it must be okay. Yeah. Does not need to be made up of 5 by 2 rectangles. Consider this. One side must clearly be a multiple of 5. The other side does not need to be even. And you could have 10 by 7 using rectangles. You would have 10 by 7, you have 10 by 17. That doesn't make, then Mn is even. Okay. This is the important thing. Okay. Because if you could tell an Mn, right, okay. What? Let G be the whatever the boundary. What? What? I mean, obviously, I can't read this. If anyone, if anyone can read this, feel free to tell me. But I can't.
Oh, by the way, I found a bug. Right, I found a bug.
Where is it?
I'm gonna fix it and I'm gonna send it again. But yeah, you can ignore my code for now.
I mean, actually, does the site take care of like rectifiable? Oh, whoa! There's just there's just a this page. Okay, I mean that would have been vastly more helpful. So basically, this is like a multi-dimensional, not quite a coloring argument. That's kind of a coloring argument. Okay. I mean, wait, no, this is a more general paper, is it not? Great, we're note to self. I was also considering trying to explore into auto tilings, but I don't think we're getting to it. I can't believe I'm using Sci-Hub because this web page wouldn't load. Oh, okay. I'm assuming.
I solved the bug and it looks like it stops at 44 for 15 by 15. I'm gonna send it again. So anyway, it's impossible. 15 is impossible.
It stops at what?
44.
Okay, so
44
everything.
block pentominoes placed.
Okay, so all but one.
Yep.
It should be available. I'm gonna send this link. Can anyone access this link, or is it just me? Ah, the fraud. Amusing. What is the change?
The bug was there's one pentomino which is blank 00 then 000. That's check underscore 3. I forgot that the top left square on that case would not be empty. The top left square of that doesn't. I don't have to check for that at all. Yeah. So I changed that one, and now it takes quite a while, but it does give you the answer to 15 within a minute.
Okay, I see. I'll leave that running in the background. Meanwhile, y'all can check that thing, that link that I sent, and if anyone can find anything. Like, check to see if you can open the link, I guess. Oh, thank you. Yeah, that's just me then. Did I just completely miss this? We need one very young person to even out. Oh, I guess I'll have to degrade myself by 2 years.
Wait, aren't we still recording?
We are still recording.
Do you want me to clip that out? Admittedly, I haven't really been paying attention for the last 10 minutes, so I don't.
I do not.
Huh?
I don't have a preference for
Okay.
whether it is clipped out.
All right. I didn't see any like names on the poll answers, so I think we're fine.
Yeah. Oh no, is this a non-English paper? Oh, great, good, thank God. Classical problem is the following. Can 25 10 label ones and fives? Okay, so that's where we're at. Okay. Introduce a variable. Okay, system of linear equations. Oh, that's obvious, right? I'm stupid. Linear algebra. I am visible by 16. X, Y, X, Y, X negative 2, Y, X negative 1, okay. What's this? Ah. So there are two methods, homology, which and the path method. Okay, where are the results? Oh, it's just a random result in the middle of the paper. The hell?
Yep. The next page has something. Yeah. The next page
Oh, 1
is
by
the
5.
end.
Wait. Oh, there are multiple pages. A 1 by 5. Ah, okay.
So the proof just ends at 147, I think.
Oh, 1%. Yeah, but I was like looking for. Yeah, I know that. Therefore, like that's a proof. But I was like, are there other results for the other things that we're considering? What? Okay, Yuri Aksinov. What is the other? What is the final other thing that we're considering? L pieces. Okay. Oh, watch out for the L piece. And it's just references. Email communication. Please have this be like some. Okay. Okay. Hopefully, I can read this quote unquote clever geometric proof. Did you proof this? Proof.
What is this? What?
Consider pentominos. That adjacent to a border with I4 part, they can't be placed interruptedly, so they can't be separated by more than one cell. So it's like a bounding kind of thing. Wait, okay. Four. Boom. Right, because that doesn't work. And place XXX. Can, but without continuation. So boundary Y pentominoes can be separated only by one cell. Ah, okay. So it's just a. The fact number 2 is even simpler. This is so true. Aksinov. Finally, I proved impossibility of tiling. Oh, this is like a computational proof, but this is somewhat faster. Dissection of rectangle into crosses. All partial crosses are covered by fixed pentominoes. The number of crosses that there is a possible. All pentominoes except border ones can be paired, so each pair covers a pair of adjacent crosses. It's an odd number of crosses. Okay, so it's a bunch of It's a bunch of casework. Right, so it's just a bunch of casework. I'll send this out, I guess, but yeah, I can also absolutely not understand like the general proof. Anyways, how are we feeling? Should we look into auto tilings, like tilings of themselves but larger, or should we end it right here?
I will probably have to get going soon.
I am going to be assuming that. Okay, I will. Okay, I don't know if there's a lot to explore about auto tilings. I'm gonna be honest, and like maybe and maybe not. So I'll look into that a bit, and if there's anything interesting, I'll schedule something. But for the meantime, I have something scheduled, which is I will probably schedule something because I think this has worked out like non-disastrous enough. I will be scheduling and can you fold every polyomino into rectangles thing, which will come up eventually, in which I will talk about folding shapes into rectangles. More on that later. More on that probably like in the actual presentation. But yes. Any parting words or additional commentary?
Thank you very much. I'm going to cut the recording right now.